So, we have a fair idea of what is effectiveness NTU method and when this can be used. This is principally used under those circumstances when we do not know what the outlet temperatures are. And instead of going through an iterative procedure for LMTD type of calculation, the epsilon NTU is a direct method which, with the help of the relations derived for many flow configurations, especially their graphical representations, would allow us to calculate the unknown temperatures, the heat transfer coefficients fairly quickly and directly from the knowledge of epsilon NTU methods. So, this class is going to be a tutorial one. We will solve one problem and see how effective this epsilon NTU method is. So, for that we take the problem where a steam at a specific pressure is being condensed, and this problem is about saturated steam which is at a pressure of 0.14 bar is condensed in a shell and tube heat exchanger. The shell and tube heat exchanger is 1-2 heat exchanger. So, one shell pass, 2 tube passes. Each tube pass would contain 130 tubes which are made of brass. The length of the tubes is 2 meters. The tube internal ID is 13.4 millimeter. The OD is 15.9 millimeter. The cooling water enters at 20 degrees centigrade. Cooling water enters the tubes at 20 degrees centigrade with a velocity equals 1.25 meter per second. The value of the overall heat transfer coefficient on the outside of the tubes, applicable for the outside of the tubes, is 13,500 watt per meter square Kelvin. What we have to find out is what is the overall heat transfer coefficient, what is the temperature of the cooling water at the outlet, and what is the rate at which steam gets condensed in this heat exchanger. So, needless to say, here we do not know, we know what is going to be the temperature of the steam since it is saturated and the pressure is provided. So, we would be able to know what is the temperature of the steam. However, one of the outlet temperatures is unknown and the steam condensation rate is also unknown. So, there is no way use of simple LMTD would give us the temperature of the cooling water. It would require an iterative procedure. On the other hand, this is a case where the steam is condensing and there is no change in temperature in that phase. So, CR is 0 and therefore, a straightforward relation between epsilon and NTU may be available. So, this is a perfect example, prime example for the use of epsilon NTU method. So, we would do that, but in order to do this we need to know some of the properties. So, for the steam which is saturated at 0.14 bar, and you can get the temperature from the steam table, which is Tsat is the temperature of the hot fluid, which is the same at the inlet and outlet, is 327 Kelvin. The value of the latent heat for condensation is 2373 kilojoule per kg. The value of the heat capacity is 1898 joule per kg Kelvin. Whereas for water, the cooling water, the specific volume is 1.005 into 10 to the power minus 3 meter cube per kg. The value of Cp, the viscosity, and the thermal conductivity, the Prandtl number, and brass, which is the material of construction of the tube, and there is significant thickness of the brass. It is not a very thin tube. The thermal conductivity of the brass is 114 watt per meter per Kelvin. Now, in order to evaluate the property of water, we only know what is the inlet temperature of the water. So, in order to find out the average temperature at which all these properties are to be calculated, we can just assume a temperature, for example, 60 degree, the temperature of the outlet water is, let us say, 50 degree. So, the average temperature would be 35, and we read all these values at 35. If after calculation you see that there is significant difference between the temperature that you have assumed and the temperature which you have obtained. So, instead of 50, if you get 90, then the properties are going to be significantly affected, and you need to do one more iteration, just one more iteration to ensure that you get the right values of the physical properties. But since it is not going to be a very strong function of temperature, so one logical choice of the outlet temperature is in the right range would give you sufficient accuracy for all design calculations. So, you need not have to, you do not take any arbitrary value, just logically take some guess value of the outlet temperature, and if your final value is not too different, then stick to it. If instead of the outlet temperature, your assumed outlet temperature of 50 degree, if you get 55 or 60, even 60, it will not make any difference in your physical properties to the extent such that your final result is going to be affected. So, that is what you have to do. So, we will start this problem of this specific case utilizing epsilon NTU, and realizing that now I have three resistances to consider. One is the the convection resistance based on the inside of the tube, the conduction resistance of the brass tube, and the convection resistance based on the outside area of the tube, for which the value of H naught is given, but the value of Hi is not given. So, therefore, we need to start from the cold water side, calculate what is its Reynolds number, use the appropriate relation, try to find out what is the value of Hi, and once I have Hi, since I know Ho and the resistance because of the brass plate, brass wall is to be included, then I would get an overall heat transfer coefficient U. So, in the expression of epsilon and NTU, in NTU the value of U would be known to me, and the value of area, heat transfer area, that is also known to me, since I know how many tubes are present and what would be the outside area for 2 meter long pipes. So, we have 132 pipes 2 meter long with known outer diameter. So, we should be able to find out what is the total heat transfer area. So, once we have the total heat transfer area and the value of the overall heat transfer coefficient, then the one side of the equation, the NTU part is known to me, the only unknown is epsilon. So, you would see how this problem can be solved. So, let us start the problem, solution of the problem, and the first thing that one has to do is to find out what is the overall heat transfer coefficient based on the outside tube area. So, this U with suffix 0, which U naught, which simply denotes is based on the outside tube area. So, this is 1 by H naught plus R naught by K ln R naught by R I. So, this is the conductive resistance plus R naught by R I times 1 by H I to the power minus 1. this is the same straightforward conduction where this 1 by twice pi R 0 U 0, where U 0 is the overall heat transfer coefficient based on the outside area, would simply be equal to 1 by twice pi R naught times H naught, which is obviously, since it is H naught, the resistance is going to be 1 by twice pi R naught. This is the area of the outside times H naught, plus you have ln R 0 by R I, the conductive resistance, by twice pi k, that is the conductive resistance, and the convective resistance on the inside would be 1 by twice pi R I H I. So, this is the relation. The overall heat transfer coefficient is the sum of the external convective resistance, and that is why R naught is here, the conduction resistance, which is 1 by twice pi k, and the resistance due to the internal convection based on the internal area. So, that is why we have 1 by twice pi R I. So, U naught is obtained out of this relation. In here, we know that Reynolds number based on diameter, and this is the inner diameter, would be rho U m d I by mu. So, when you plug in the values at 1.005 into 10 to the power minus 3 to the power minus 1, which is where rho is simply 1 by V f, and the V f is known over here, times U m is 1.25, and the di is 13.4 into 10 to the power minus 3, and the mu value, the viscosity, is 769 into 10 to the power minus 6. So, this would turn out to be 21,673. So, obviously, it is a laminar, it is a turbulent flow, and it is fully developed based on whatever we have studied for that case. So, I am going to use Dittes-Boelter equation, and the Dittes-Boelter equation would simply give you Nusselt number based on the diameter is H I d I by K f, which would be equal to 0.023, Reynolds number to the power 0.8, Prandtl number to the power 0.4, because this is where the outside wall is being, the tube wall is the hot one, and the cold fluid is flowing through the tube. So, that is why the exponent will be equal to 0.4, and when you plug in all these values, this would be equal to 131, and from this, from the Nusselt number from the Nusselt number based on the inside diameter, which is H I d I by K f, since this is equal to 131, you should be able to calculate what is the value of H I, which is 0.62 by d I, which is 13.4 into 10 to the power minus 3 times 131. So, it would be 6057 watt per meter square Kelvin. So, that is the value of H I. So, what is U naught? Putting into the value of, the only unknown here is H I, because the thermal conductivity is known, the geometric parameters are known, H naught value is known. So, U naught can simply be calculated as 1 by H I, which is 13,500 plus 15.9 into 10 to the power minus 3 by K is 115, and ln of 5.9 by 13.4 plus, just putting in the values, nothing else. So, the value of the heat transfer coefficient, overall heat transfer coefficient, would turn out to be 3549 watt per meter square Kelvin. So, now I have obtained what is the average value, what is the overall heat transfer coefficient based on the outside area. Now, to find the outlet temperature, so one part of the problem is over. To find the outlet temperature of water, we need to use epsilon NTU method. So, how am I going to use epsilon NTU method? The total amount of heat transfer would be C of C times TCO, temperature of the cold fluid at the outlet, minus TCI. So, TCO would be equal to TCI plus Q by Cc. So, that is the relation which we have to find out. Now, this Q is to be obtained. So, this is the outlet temperature, but I do not know the outlet temperature, I only know the inlet temperature. So, TCI and THI, which is equal to THO, this is known to me. So, how do I do this? My Q, the total amount of heat transfer, would be effectiveness times Q max. So, this is the definition of the effectiveness epsilon, where Q, the actual heat transferred, is epsilon times the maximum heat which is transferred. So, what is the maximum heat that is transferred? It is equal to T C minimum by THI minus THO. So, that is the maximum, that is the way you calculate this. So, minimum, so therefore, the minimum capacity rate is that of the cold water as CH tends to infinity. So, capacity of the hot fluid, since it's steam condensing on the outside, will obviously be equal, will obviously tend to infinity. So, therefore, we are dealing with a situation in which CR is equal to 0. So, that would allow us to use a simple relation between epsilon and NTU, and since NTU is known, we should be able to calculate epsilon, and from epsilon we can calculate Q, and from Q we can calculate what is TCO. So, those are the steps which I am going to follow one after the other. So, with CH tends to infinity, my C minimum is going to be C of the cold water, and C of the cold water is m dot Cp, all related to cold water. So, what is m dot? Is rho A um. This is the flow rate of water through one tube. I have n number of tubes which are present in here. So, I am going to write the rho as kg per meter cube. The area would simply be the cross sectional area 0.0134 whole square. So, pi d square by 4, this is meter square, into 1.25 meter per second, that is the velocity, into 130 number of tubes which are present per tube pass. So, the mass flow rate of water would simply turn out to be 22.8 kg per second. So, my C minimum is 22.8 kg per second into 4178 joule per kg per Kelvin, which is 95270 watt per Kelvin. So, this is the value of C minimum that we have obtained. So, now what is NTU? I have all the values required for NTU, because NTU is defined as U naught A naught by C minimum. That is the definition of NTU. I have C minimum over here. I have calculated what is U naught in the previous calculation, and therefore, I can find out what is NTU. So, NTU being defined as U naught A naught by C minimum which in this case would be 3549 is U naught. The area would be this is the not the cross sectional area, this is the area available for convective heat transfer. The area available for convective heat transfer would be pi times d, which is 0.159. This d is the outside diameter, because that is the area which is available for heat transfer, times the length. So, this is pi d o l. So, that is the area multiplied by the number of tubes. So, this is n into 2, this is the number of passes. Okay. So, just be careful about using while calculating the overall area for heat transfer. The total area for heat transfer would be the outside area of one tube multiplied by the number of tubes per pass and the total number of passes, because when you do that, only then you get the total heat transfer area in the heat exchanger, considering all tubes, considering one tube, considering all tubes, and considering all number of all passes. So, the total would give you the total surface area available for heat transfer, which is by definition A naught in NTU. So, NTU is U naught, A naught. So, I know I have already calculated U naught. I now know what is A naught, and the C minimum I have calculated in the previous slide. So, this C minimum is simply going to be the one which we have calculated earlier. So, this NTU would be 0.968. So, from the figure of epsilon versus NTU. So, let us now look at the figure that we have over here. If you look at the numbers over here, we are dealing with a shell and tube heat exchanger with 1-2 arrangement. So, this is a parallel flow heat exchanger, this is a counter flow heat exchanger, this is a shell and tube heat exchanger with one shell and any multiple of 2 tube passes. So, we have the first case, which is 1 shell 2 tube passes, and the value of NTU we just calculated is about 0.968, which is about 1, and we need to find out what is the value of epsilon for such a case. So, from NTU equal to 1, since my CR is 0, we go all the way up to this point and come over here and find epsilon. So, with a known value of NTU to be equal to 0.968, we go up to the curve, which is C minimum by C maximum equal to 0, which should be the case for condensers and boilers, and we read what is the value of epsilon. So, this value of epsilon is going to be slightly more than 0.6. Let us take the epsilon to be equal to 0.62. So, knowing the value of NTU, knowing the ratio of C minimum by C maximum, we find out what is the value of epsilon. So, the value of epsilon that we obtained from here, from the figure or from the graph for epsilon versus NTU, NTU is equal to 0.968 and C minimum by C max, since it is condensing, to be equal to 0, epsilon would be equal to 0.62. So, the next part is straightforward. TCO is TCI plus epsilon C minimum THI minus TCI by CC. This is just the definition of epsilon over here. So, when you put the values in here, this would be 20 plus 0.62. C minimum is Cc, so they will cancel out, and THI minus TCI is the temperature of the steam minus the temperature of the water, cooling water which is coming in. So, your TCO to be equal to 41.1 centigrade. So, our assumption of the temperature to be equal to 50, the outlet temperature to be equal to 50 is not a bad one, which we have used to calculate all the physical properties. So, since it's okay, it's not too different from our assumed values. So, we will stick to this value and proceed ahead. Instead of assumed 50, if it comes to be maybe 75 or so, then we have to go do one more iteration. But 50 and 41 is not that different, and all the properties that we have taken for water are not that sensitive to temperature change, and therefore, this is a reasonably good assumption and we can proceed with this. So, the second part of the problem is also over. We have calculated what is the temperature of the cooling water outlet, which was not possible using LMTD without a substantial iteration. So, epsilon NTU methods clearly gave us a simple way to tackle the problem of knowing the outlet temperature of the cold fluid. The third one which is remaining is what is the condensation rate of the steam. So, let us do the last part over here. The condensation rate of the steam which is let us say m dot of the hot fluid is simply Q by HFG, and since I know epsilon, I can find out everything is known to me, TCO is known to me, TCI is known to me. So, the outlet temperatures are known, multiplied by Cc would give me Q divided by HFG, in which is Cc is 95270 watt per Kelvin, which is this one, times TCO is 41.1, TCI is 20, and the value of this, so this is Kelvin, and the value of HFG is 2373. That is the latent heat of that's the latent heat into 10 to the power 3 joule per kg Kelvin, and this would result in a value of m dot to be equals 0.85 kg per second. So, that is the condensation rate of steam. So, this problem, which the tutorial problem which we have solved in the class, clearly shows the advantage of the epsilon NTU method. So, the idea would be to obtain NTU and then read the value of epsilon. In order to obtain the NTU, in order to calculate the NTU, you need to calculate the overall heat transfer coefficient, which is U. You need to know what is the total area available for heat transfer, which is A naught, and you also have to have an idea of what is the value of C minimum, that is m dot Cp of the minimum value of m dot Cp between the two streams. Once you do that, the value of NTU is known to you, and depending on what kind of heat exchanger you are dealing with, is it a parallel flow 1-1 heat exchanger, counter flow 1-1 heat exchanger, if it is a single cell multiple tube passes or multiple shell multiple tube passes, for all of them there are curves available in your textbook which would be provided to you provided these kind of questions come. So, these graphs would be provided to you, and then from calculating the value of NTU and reading the corresponding value of epsilon corresponding to a specific ratio of CR, you would be able to obtain the effectiveness, the value of the effectiveness epsilon of a heat exchanger. And once epsilon is known, then you can use simply the definition of epsilon to evaluate what are the outlet temperatures, what are the temperatures of the two outlet streams, and once you have that, then the total amount of heat transfer, the calculation of total amount of heat transfer is fairly straightforward. So, I hope you understood the concept of effectiveness, how epsilon NTU method can be used for the design, especially for the evaluation of the unknown values of the outlet streams and so on. We would solve one more problem on epsilon NTU method as tutorial and then move on to the next topic.